Another typical problem dealing with ideal gases is the calculation of the gas density. This will be a useful number for comparison of gases to liquids and solids. Indeed, density is, in a way, a measure of how far apart molecules are in a given substance. Most organic compounds have densities in the vicinity of that of water, about 1 gram per cubic centimeter or 1 gram per milliliter. Gases, on the other hand, have significantly lower densities, often 3 orders of magnitude smaller. Here we are asked to determine the temperature in Kelvin at which the gas exhibits a density of 0.66 gram per liter under a pressure of 1.00 atmospheres. You are also told to assume the ideal gas law. You should first transform the information given in the text form into mathematical form with the appropriate symbols and units for each property. So we write D, the density, equals 0.66 gram per liter. Then we write P, the pressure, equals 1.00 atmospheres. While this information is not directly given to you, you should recognize that you are also given the molar mass of the gas, since you know that you are dealing with neon. So we write molar mass, M, equals 20.18 grams per mole. Then you write the mathematical representation of the ideal gas law as PV equals nRT. Obviously, you quickly realize that it will take a little work to solve this problem because you are missing both the volume and the number of moles to derive the temperature from the ideal gas law. At this point, I would like you to note that the properties given in this problem, density, pressure, and molar mass, are all intensive properties. That is, these properties are all independent of the amount of gas. The quantity you need to calculate is the temperature. This is another intensive property. So, to solve this problem, you could assume any number of moles of gas. Why? Simply because the quantity of interest, being intensive, is independent of the size of the system. Let us say you want to keep things as simple as possible, and you choose n equals 1 mole. Using this number of moles, you can now calculate the mass of 1 mole of neon using the molar mass of neon. Once you have the mass of gas and the density of the gas, you could calculate the volume of the gas, since volume equals mass divided by density. Now you have the volume, the number of moles, and the pressure of the gas. So using the ideal gas law, you could calculate the absolute temperature of the gas. You should try this approach for the sake of practice. I'm not actually going to solve this problem in that fashion. I'm going to show you how to manipulate equations so you end up with an expression of the temperature in terms of what you are given in the text, the pressure, the density, and the molar mass. The advantage of this approach is that it minimizes the number of calculations, since you only calculate what you need, the temperature, using what you're given, the pressure, the density, and the molar mass. Indeed, why calculate the volume of the gas if you're not asked for it? The more calculations you carry out, the more chances for errors. So, let us see how we can proceed. First, we need to relate the quantities given in the text and not involved in the ideal gas law to quantities that appear in the ideal gas law. So we write gas density equals mass of gas divided by volume of gas, or D is equal to M divided by V. While V is in the ideal gas law, M is not. So we replace M, the mass, by the product of the molar mass, M, and the number of moles, N. Or lowercase m equals N times uppercase M. So we can express the density D as the product of Nm divided by the volume V. We rewrite this equation as N divided by V equals to D divided by M. We can also rewrite the ideal gas law PV equals nRT as N divided by V equals P divided by RT. We can now combine these two equalities and obtain D divided by M equals P divided by RT. We have thus obtained an expression relating the gas density, its molar mass, its pressure and temperature, and the gas constant. This equation can be rewritten as T equals P times M divided by D times R. Now we can obtain the value of T. Note that to be certain to get T in SI units, that is in Kelvin, it would be advisable to express each of the other properties in SI units. So we will write the pressure in pascals, the density in kilogram per cubic meter, the molar mass in kilogram per mole, and the gas constant R as 8.3145 joules per mole Kelvin. Note the use of conversion factors for the pressure from atmospheres to Pascal and for the density from gram per liter to kilogram per cubic meter. All units cancel out. Recall that Pascal times cubic meter is a joule, and you are left with a property expressed in Kelvin. You obtained T equals 372.6 Kelvin, which you must round off to 370 Kelvin, since the density in this problem is only given with two significant figures.